When a software engineer first looks at Verilog, the syntax feels remarkably familiar. It looks like C, it reads like C. But assuming it executes like C is a guaranteed way to break a design. In a traditional programming language, a subroutine is simply an isolated thread of logic. The processor reads it, executes it line by line, and returns a result. Hardware description languages do not operate in a sequential vacuum. A Verilog module is a mathematical representation of a physical circuit. Every wire is connected, and logic gates evaluate concurrently. Directly porting sequential logic often triggers a cascade of simulation-synthesis mismatches, producing RTL that defies physical realization. To safely abstract logic in hardware, you must unlearn software sequencing. You have to divide your subroutines into two distinct categories, separated entirely by how they interact with simulation time. The IEEE 1364 standard provides two distinct structural subroutines to handle this: the function and the task. On the left, a Verilog function operates under strict temporal constraints, executing its entire logic block in exactly 0 simulation time. On the right, a Verilog task is entirely time-aware. It can pause execution, wait for specific clock cycles, and then resume. The compiler evaluates these two time relationships and maps them to physical hardware in entirely different ways. A subroutine's ability, or inability, to manipulate the clock dictates its mathematical mapping rules, port configurations, and exactly where it belongs in your system architecture. Because a function operates instantly, its input and output constraints are highly rigid. It takes a set of input values, evaluates them, and returns exactly one single result. This diagram of an IEEE standard function shows the exact port rules in action. A function must contain at least one input declaration, but is absolutely prohibited from containing any output or in-out arguments. Notice the implicit return mechanism. The final output value is assigned directly to a variable matching the function's name. This restriction exists because a function maps directly to instant combinational logic. It is physically impossible for an instant logic gate to delay a signal. Therefore, a function cannot contain any delay hashes, event at symbols, or wait statements. Engineers rely on functions to model expression-level circuits. Address decoders, multiplexers, and arithmetic ALUs all utilize functions because they must resolve their logic within a single continuous clock cycle. There is also a secondary compile time application. Introduced in the Verilog 2001 standard, a constant function calculates parameterized register widths during the elaboration phase, before the simulation even begins ticking. Functions operate as pure mathematical equations. They are instantaneous, highly predictable, and rigidly structured for physical synthesis. A task, conversely, is a procedural subroutine designed to drive sequences across multiple clock cycles. The structural input-output constraints are stripped away. A task can be declared with 0, 1, or dozens of input, output, and in-out arguments. It does not return a single value through its identifier. Instead, a task passes multiple data results back by actively driving its designated output ports. Looking at this traffic light sequencer, we clearly see the time manipulation capabilities. A task freely utilizes delay statements, shown here as #100, and event triggers like @pauseEdge clock. When a module enables a task, the simulation timeline hits that subroutine and freezes. The enabling process is completely suspended until the task finishes processing its internal delays and returns control. This timeline suspension is required for driving sequential state machine behaviors, generating clock waveforms in a test environment, and processing asynchronous hardware resets. Tasks operate as time managers. They orchestrate the flow of data across the temporal boundaries of your entire simulation. When these two constructs interact within the same module hierarchy, their temporal capabilities dictate a strict set of dependency rules. As this dependency tree illustrates, a function is strictly barred from enabling a task. Attempting this causes a syntax error. Because a function resolves instantly, it cannot invoke a subroutine that can pause the timeline. Reverse the relationship, however, and the compiler accepts it. A task calling a function is a standard design pattern. The task simply pauses its timeline progression, evaluates the instantaneous combinational logic of the function, retrieves the result, and then resumes waiting for its next scheduled clock edge. Temporal constraints dictate a one-way hierarchy. Time-consuming containers can utilize instantaneous math, but instant math cannot wait for time. There is a hidden memory hazard here for engineers porting over from software. By default, all variables defined within Verilog tasks and functions are statically allocated. Because of this static allocation, if a task is called concurrently from two different always blocks, both instances attempt to write to the exact same shared memory address. Data simply overwrites itself. The IEEE 1364-2001 standard provided a direct solution, the automatic keyword. By explicitly declaring an automatic task or automatic function, you instruct the compiler to dynamically allocate unique memory space. In this recursive factorial function, a new memory block is generated for each pass, stacking cleanly without corrupting previous data. This dynamic allocation mechanism is an absolute requirement to build reentrant test bench tasks or recursive mathematical functions. Understanding how the compiler assigns memory prevents catastrophic data corruption when scaling subroutines across highly concurrent simulation environments. So, where do these subroutines belong in a professional project directory? Inside the synthesizable RTL domain, the code that actually becomes silicon, you will rely predominantly on functions to construct the ALUs, address decoders, and combinational data paths. Outside of that core logic sits the test bench domain. Here, the external simulation environment relies heavily on tasks to open files, generate clock cycles, and inject controlled stimuli into the design. We can see this dynamic in this terminal readout. The task-driven test bench is pumping data vectors into the compiled logic and generating a VCD dump file to track the resulting waveforms. In practice, functions build the physical chip. Tasks build the virtual laboratory used to test it. This summary table maps out the strict boundaries. Functions execute in 0 time, return a single value, and model combinational logic. Tasks consume time, drive multiple outputs, and model complex behavioral sequences. Verilog subroutines are not C functions. Treating them like sequential software threads will break your simulation. Hardware abstraction serves a structural purpose, defining exactly how a block of logic integrates with the clock and the physical memory of the chip. Choosing between a task and a function is the decisive act of setting the temporal boundaries and physical realities of your silicon model.